Thank you to the organizers for inviting me here. I know this is a long-waited talk. I mean, this is like a debt I had with the organizers because it's been like almost 2 years and I haven't presented here. So now I'm here to pay that debt. Um, I'm gonna talk, like we said, of this orthogonal polynomial-based kernel for support vector machines. And I'm going to talk about this recent work we have been developing in the past few months with Luis Carlos Padierna from Universidad de Guanajuato and Luis Garza from Universidad de Colima. Um, First, I'm going to start with a brief introduction for or of the concepts we're going to need in the talk. Then I'm going to present some of the use orthogonal polynomials have had in machine learning and the implementation of these kernels based on orthogonal polynomials, which is our like the main work. I'm going to make some conclusion and present some references. Uh, well, this is like the standard theory of orthogonal polynomials. We consider a broad measure in some real interval, and we can define this inner product, and we have that for absolutely continuous measures, the moments can be represented by an integral, and they are finite and exist. And we can always use the Gram-Schmidt process to construct real orthogonal polynomials in that way. Here are the orthogonality conditions. This means that they are zero when the degrees are different, and something different from zero when they have the same degree. Here, this is the Kronecker delta, and this is some constant. Uh, we all, or many of us, know the classical orthogonal families, which are the Jacobi, Laguerre, and Hermite. These families appear in many contexts in mathematics and engineering, and they have some associated function and in some interval or subset of the real line, and they present some parameters here which have to be given in this way. Then they are important because they satisfy many properties. Some of the more relevant is that they satisfy a Rodriguez type formula given here. Also, the derivatives of classical orthogonal polynomials constitute another family of orthogonal polynomials. And they satisfy a second order differential equation, even in this way, with some degrees for these polynomial coefficients. And this is called the Hans property. And they are also related with probability distributions in this way. The Jacobi polynomials are related to the beta distribution, the Hermite with the normal, and the Laguerre with the gamma distribution. Also, I'm going to present here the definition of discrete measure and discrete orthogonal polynomials. In this case, these discrete orthogonal polynomials are defined in, in a discrete set of points. We can construct a discrete inner product, and the orthogonality is defined against that inner product. and they are orthogonal with respect to some weight function or a set of weights. The discrete measure is given in this way, where these are the points that belong to the support of the measure. Delta here is the Dirac delta, and usually these weights are positive. So the support of this measure will be exactly this n, capital N points. We also have these classical families where we have this definition for the discrete measure, and depending on the family we're considering, the weights are given explicitly, and the m also is a number, or in this case, we consider infinite terms, and this p or a or c, the parameters obey these restrictions. Well, now this support vector machine is a machine learning model that basically wants to classify in a set of points, distinguish between the classes we have. No, in this image, we can see that we have a like a cloud of points where we have some red points which belongs to one class and some blue points from another class, and we can see that they are not linearly uh, um, separable. So here's where the support vector machine comes in. The idea is to take these points to a higher dimension and make them separable with a hyperplane, like in this picture. And we send these given points to a space where we have the features of the, or the, yeah, I always see them as every column of your data, and we make this uh, now new set of points separable with a hyperplane. And for this, the support vector machines use something called the kernel trick. This means that you don't have to explicitly give the linear transformation because that will be numerically costly. And the kernel trick is that you can obtain the same results by using this kernel function where you construct like a gram matrix, which is a symmetric matrix, and you evaluate the kernels, and those evaluation give you like this distribution, or these values, let's say. This gives you like a less computation, yeah, less computational cost, and you don't have to explicitly compute the transformation of this point to that higher dimensional space. And the main property or advantage is that you can use them for when you have this like non-linear distribution, let's say. So these kernels have a function in the core, and The most commonly used are the linear, the polynomial functions, and something called a radial basis function, among others. And the thing is, in applications, they always use these like kinds of functions. So the idea is, let me, oh, I forgot this. The idea is to use some kernel based on a specific family of polynomials to construct that support vector machine and trying to improve the results, as I'm going to show you later. But before that, let me just say that the kernel functions that are used in these support vector machines have to satisfy this so-called Mercer theorem when it has two conditions. The number one is that the kernel must be symmetric, and the other condition is that it has to be positive semi-definite. That's why I said that we are always going to consider the Gram matrix, and given in this way. And when we consider this matrix, we can see the conditions as this in this matrix form. So for any vector, this will imply that our our matrix satisfy this positive semi-definite condition. Now, this is a problem that has been studied for many years now. Like I said, they use some specific families of orthogonal polynomials, like the most known in the uh, engineering world, let's say, like Chebyshev, Legendre, Jacobi, Hermite, Laguerre. But recently, well, in 2018, Luis Padierna proposed this Bauer-based kernel, and it obtained some very good results. So he made a comparison with the like, let's say, state-of-the-art kernels, and he obtained very good results. One of the advantage he saw is that this kernel based on Bauer polynomials requires less support vectors. A support vector is like in this picture, like the vectors that make that boundary, that frontier between the classes of data. So constructed in this way, the kernel and the algorithm of the SVM require fewer support vectors, which is a good thing because it saves computationally. Now, what we want to do is to use this approach of Padierna to construct a, a kernel and function based on orthogonal polynomials, and our goal is to improve the classification. We're going to use this to classify some set of data, and we want to know how the structure of the data uh, like fits the orthogonality, something like that. And for this, we have made some approaches. The first one, we construct a Cernic kernel. A kernel based on Cernic polynomials. Here I put the definition of Cernic polynomial. This is for even degree or odd degree, and the case when m is equal to 0, is called the spherical Cernic polynomials. This radial part of the polynomial is given in this way. So we take these Cernic polynomials and we construct a kernel using them. Let me, in this way, these are general functions. Here, these 5 functions are based on the Cernic polynomials. We implemented this in MATLAB, and we use some data set given in this base Oasis 1. This data set is a set of images of brains, and we want to classify the subjects, the people, in sane or a person who has this Alzheimer's disease. So that was our goal. I have to say that this first approach was made with some students in my university. It was challenging because they are all of them are in engineering programs, so they don't have like a very good basis in mathematics, but they are very good students, and they were able to pull this off. Uh, and we construct that this kernel based on Cernic polynomials. We implemented the support vector machine, which is this algorithm to classify. From the images, we extract different features. The ones we start with only 3 features, which were the gray matter, the white matter, and the some liquid we have in between the skull and the brain. Um, and using those features uh, with the SVM, with this kernel, we obtain these results. Here, we compare with the most common kernels, and one of the important metrics is the accuracy, which is how well your classification is made. We can see that the Cernic is the lowest, and then we have this sensitivity, which is how well, I mean, how many true positives you classify, which is again lowest. But now then we have the specificity, which is the true negatives, and here it belongs. I mean, it has the best result. This can be useful depending on your uh, classification, because you may want to have a best the best classification for negatives, because it will be like more I don't know, how to say it, but it's better to make a mistake here than make a mistake with through a false positive. Um, and the other metric is this PSB, which is the proportion of support vectors. It gives an idea of how many support vectors you need to construct that boundary between the classes. And well, we have the result. We draw these conclusions, like I was saying. Um the metrics are comparable, so we were happy actually to get the results. And I forgot to say that we use these Cernic polynomials because of the geometry of the image. Uh, we first take the data and map it to the unit disk, and then we make all the procedure of the classification. But it was like a hunch. We use this just to like a start point, a starting point, and 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 well, we have some decent results. Um, the comparison was in accuracy a bit lower, but still acceptable. And then we focus on improving the data set, because that's one of the main problems when you work with data, that the data set is always tricky, let's say. You always have like missing values, or uh, you have to make some treatment to the data in order to produce good results. And the other thing we are still working on is uh, another kernels, and adjusting the parameters of this certain kernel, which is basically the degree we are using to construct the kernel function. Now we also study another approach for constructing kernels. Here I present this book from Jim Bernard Lasser, Edward Powells, and Mihai Putner. This book, I think, is from 2022, and they give uh, some like instructions to analyze clouds of points. So when they say, when you have to fix a polynomial degree and define this number, then you construct a vector where every entry is given in this way, the monomials in this form. You construct some matrix, the same matrix, where each row is exactly this vector of monomials, and you construct this M matrix in this way, define this mapping from X to a polynomial in this way, and they say plot the level sets even this way for some values of gamma, and pay attention to this specific value. So when one does that to any cloud of points, you get some result like this. And the idea they present is that doing this, you can see that the red level set like capture the density of the points. I mean, most of the points are enclosed in that red curve. So they say that this gives you an idea of how this empirical probability measure constructed with the points, and actually with a fraction of your points, uh, and you can like see exactly where uh, they are, and what's like the distribution. Um, you have a polynomial which is related to this cloud of points, we using this symmetric matrix we defined before, and here the empirical measure is constructed, like I say, with a fraction of the point using the Dirac delta. The matrix is given explicitly, and they say that this idea may have some applications in data analysis. Particularly, they say it can be used to detect outliers, because if you can see or where most of the points are, all the points that stay outside of this red line can be treated as outliers. Um, and also they say that you can have an idea of the shape of the support of the measure. Um, they also say that when you consider this polynomial minus one, it is the Christoffel function, which is associated with the Christoffel-Darboux kernel. So taking this as a starting point, we thought of this method to construct custom kernel based on the data. And we expect that when you construct a kernel, well, first you have to construct the measure with some um, set of the points, subset of the points, and then you construct like an inner product, and using Gram-Schmidt, you can construct the polynomials. And with those polynomials, you can construct the kernel to use it with the SVM, the support vector machine. The idea is that since we're constructing the polynomials using the points, they might be able to capture the structure and describe them better. So that's our hope. And this is the procedure I I talk about. You first take a percentage of the whole points set, and you construct the measure. You construct an inner product with that measure, and apply Gram-Schmidt. With that polynomials, you can construct a kernel in this way. This is the Gram matrix. This is the some vectors evaluated in the data. The one of the things of the kernels is that they give you this idea of how far a pair of points are, and that is how it can be useful for classification. So when you get a result, a small number, it means that the points are far away, and reciprocally, when you give a big number, it means that the points are close. So using this, we try it on a specific data set, which is called a 4 class. This is a cloud of points which are non-linearly separable, and it has only two features, two classes, let's say. With each class, we construct a family of orthogonal polynomials, given here by P and Q. And then with those polynomials, we construct the kernel. This kernel, since we're considering positive measures, and we have a result that says that if you construct, you have two kernels and you multiply them, it's still you get, I mean, you get still a kernel, a valid kernel, meaning that it satisfies the Mercer's conditions I show you before. So we construct the kernel in this way, like with the product of these polynomials families, and we take this 4 class data set, we standardize the data to be in, I think between -1 and 1, and we run like the algorithm. You have to take some set for training the algorithm and some other set to validate that it works. We use, I believe, 80 and 20% for 80 for the trained and 20 for the test. And and we have these results. Here is the picture of the points. You can see that it has only two classes, and using this approach, we get an accuracy of 1, meaning that every point was correctly classified. Uh, and you can see here the decision boundary for each class. So these lines represent that. This was also studied by Padierna, so we compare this dataset with many other kernels, the radial basis function. I don't remember the name of this. The linear kernel, polynomial kernel, based on Legendre, based on Chebyshev, and you can see that we got a result similar to the best we can get. So this was like a good sign. Also, we use this approach to study again this Alzheimer's disease classification I told you about. Now, in this case, we take 6% of our data. Like I said, we had 3 features, and we constructed a polynomial family for each feature, and with those polynomials, we construct the kernel. And we run again the algorithm. And now the results were a little bit better. Here, you can see that I only left here the radial basis, the linear kernel, and the Cernic, and I call it discreto because it was based on a discrete measure. And we can see that the accuracy improved. The sensitivity was the lowest, but the specificity was greater. And also the proportion of support vectors is lower, which is a good thing, meaning that it needs less support vectors to make that boundary. And well, I added metric, which give you an idea of how far from coin toss is your prediction. So this it has the best among these kernels, the best behavior. And so, as a conclusion, I can say that we implemented these custom kernels based on orthogonal polynomial families using known families like the Cernic polynomials and constructing the polynomial sequences from the data, a fraction of the data. We can see that when we construct the families, the polynomial families from the data, it captures the geometry of the space where the points live, and that helps to make it like more accurate and that it needs less support vectors to draw the boundary line. And so we still have a lot of work to do. We're still thinking about how we can take this to a set of data that has more features, more columns, let's say. How will that work? Maybe we were thinking, Luis especially, about using multivariate orthogonal polynomials, and we're still working in that. But for now, I think this is all. Let me just talk about some open problems we can see. Um, the overfitting is always a problem in these machine learning algorithms. We run some tests to see if the results we obtained were actually good or they were because, I mean, the accuracy of one was achieved by overfitting, but it turns out it doesn't. So we have like a good result. Also, we're still thinking about considering cross interactions, which is considering terms with a mixture of features of columns, let's say, and explore how that kernel would work. Uh, Also, the computational cost, it wasn't a problem here, but maybe when we consider larger data sets, this can become a problem because since we have to make the inversion of a matrix, that can be computationally costly. Also, this aspect of noise sensitivity, um, see how this empirical measure can be affected by outliers. In this work, we have been using like a random sample of the data, but what if in that sample we have like many outliers that can affect or may affect our results? And also the scalability, like I said, uh, how to extend this to more dimensions. And that's where we were thinking about uh, multivariable orthogonal polynomials, so maybe matrix orthogonal polynomials. We don't have uh, any any examples in that way, any experiments, but I think that is all. Here are some references. This paper from Padierna is where he introduces the Bauer family for constructing the kernel. He also has a paper where they use this approach to analyze images of food, feet, to determine if it has diabetes disease. And this is the reference of the book I show you. And this is another important book about kernel constructed via orthogonal polynomials. So if any of you are interested in this topic, we welcome you and encourage you to contact us because I think this is a promising field that can be uh, interesting for some of you, I hope. And well, thank you.